we now start talking about a different architecture. So far, we've talked about a simple neural network, a convolutional neural network, and now we're going to talk about what are known as recurrent neural networks. So the first thing that we need to understand is that हमारे पास मुख्तलिफ तरीके के data अभी तक हमने देखे हैं. We've seen data of different types, right? So the first type of data that we saw was the example of the MPG where you were simply doing regression, right? This was the MPG data. We also saw another example of iris classification, and there also you had a bunch of data and you need to classify, right? In the second example that we had images, all right? So what was different about the images as compared to the earlier data sets that we saw, the first two data sets that we saw in which you were doing regression and classification? Can you think structurally what was different about images as compared to these first two? Sorry? Okay, so this is two-dimensional. That's one difference, all right? So you had 2D images, and they had to be converted to 1D before we could actually work with them, right? That's one important difference. What others?
The features were not given in images, or इसमें features given है.
इसमें जो features हैं, those are in the form of images. And here the features are not in terms of images. Okay. ठीक है. Anything else that is okay, so think about this. If you look at the rows over here, row number 1, all right, and row number 0, in both of these, whether it's iris or whether it's the MPG example, okay, and you think about an image. So let's say you have an image of a person, all right? Now, and you've converted this into a one-dimensional image. And now you have two rows over here, one row over here and one row over here, okay? Now, by a row, I mean that you have inputs and outputs labels as well. Now, what if we swap these two? If we swap these two, or if we swap the data, the rows in the iris example, do you think it will have any impact on the results? It should not have any impact, right? Because these are more or less independent of each other. Now, what about the image? If we swapped this particular row with this particular row, okay, or if you look at this, if we swap this particular row with another row over here, would that have an impact? Okay, that would have a huge impact, right? Because essentially what you're saying is you're distorting the image. So there is a relationship between the image rows, whereas in the other cases, there was no relationship between the rows, okay? Now, because of that, the technique that we used was different, okay? So what was fundamentally different between the technique that we used over here and the technique that we used over here? We had 2D filters, right? So we used something called convolution, all right? And convolution, especially in 2D, was basically saying that we take an image, all right? And we're putting a filter over here, okay? And that filter is looking at the relationship between the rows over here, between the adjacent pixels, right? So we've looked at all kinds of filters. We looked at filters which were doing edge detection and blurring and so on. So it was actually looking at the relationship of the rows and the columns in that particular data, okay? So this was a fundamental difference between the image data where we're using convolution and where we were not using convolution, okay? Now, there can be a third type of data as well, okay? And these are third type of data, as you mentioned. This could be, for example, audio. Did you say audio? Yeah. So for example, if you have audio, now can you tell me what's the difference between, let's say, the first type of data and the second type of data, which is images, and the third type, which is, let's say, audio data. So you have speech, you have somebody speaking, all right? And this is, what's the difference between these three? On time, all right? So the very critical thing that comes in is that there is a time dependency, okay? So what I'm saying right now, if I'm saying, hello, how are you, whatever, what I'm saying at the end, how are you, is dependent on what I've said earlier, all right? So if you're trying to predict, how, what I would say at the end of that sentence, clearly that depends on what happened in the past, okay? So there's an additional element in here. So earlier there was, the 2D spatial images had a relationship. Here there was no relationship between the rows. You could scramble them, you could shuffle them, it would have no impact. Here, if you shuffle the data, it would have a completely big impact. And here what you're seeing is that there is, in addition, so suppose that you had a series of images, okay, you're taking a video. So audio was a little different, but let's continue with the video images. So you had a sequence of images and you're taking images, and now you're capturing still images, you're taking frames per frames. And now let's say that you had, in the first frame, you had a cat, okay? And a second, split second later, you took another image and you're trying to predict that. Now, let's say if your prediction engine came up with a human being over there, would that make sense? That, if it's going 25 frames per second, is it possible that, this cat suddenly transformed into a human being? No, it's not possible, because, it's a video of it could be that it's a different image altogether, but the likelihood is that that particular sequence of video is continuing on uninterrupted, okay? So if you were trying to do a probabilistic analysis and it gave you two images, in one you had another cat and another you had a human being, which is more likely? The one with the cat, right? Simply because you've already determined that the previous image had a cat. So now the images have a time dependency as well, and what is happening in time t+1 depends on time t, okay? So this is where you need to come up with earlier we came up with the concept of convolution to be able to address images, okay? Now we have to come up with a completely new technique, okay? And the question is, what kind of technique should there be? So you can see that there was no relationship over here. You can see that if you have this cat over here, clearly if you swap these two rows over here, obviously this image would get completely messed up, okay? Now the question is that if we have time dependence data, then how can you change your neural network? You've got a neural network, all right? You've got X, and you've got a neural network over here, and you're getting a Y. Now, how should we change the neural network so that now the time dependence can be included? How should we do that? So there should be some feedback, you're saying, okay? So what you could have is some feedback over here, which is basically saying that, okay, feedback hona chahiye. Any other ideas? How would you take into account that the next image that is coming in? So let's say we're getting a stream of images, okay? First of all, that now that we have time, should we introduce a new parameter in the data? Abhi tak humne kya kaha tha? Data was basically x0 se lekar ke xn tak tha, right? This was a bunch of data, and it was a still data. It could correspond to a particular still image, okay? Now what we're saying is that we're getting another image, okay? And it also has the same size, okay? It also has x0 se lekar ke xn tak. How do we differentiate between these two? Let's introduce a time domain now. So we're going to introduce a time domain. And because of that, I'm going to actually now change this a little bit. I'm going to put in, I'm going to use x0 से लेके xn तक इस तरह मैं दिखाऊंगा. And on the bottom axis at the subscript, I'm going to indicate time, okay, because this is now the standard notation. So you're going to have, this was the original at time t. Now you've got another set of x0 से लेकर के xn तक. Now what will this be? Time t plus 1. Okay, so this will be time t plus 1. So you can now see that we've got a series of images coming in, and they have a sub new parameter, which is now time. Okay. जी. So देखें, आपका ये एक image था. You took this at time t is equal to time. Let's say t is equal to 0 seconds. Okay, you started your stopwatch, and then 1 second later, time t is equal to 1. You took another image. Okay, and clearly that is also going to present this whole set of data. Okay, so if this was, let's say, a 10 by 10 image, this would be 100 parameter, 100 inputs. This would also be 10 by 10, but now it would be a different image. And as I said, these two are related, okay, because this would be, let's say you took an image and then 1 second later you took another image of the same room. Okay, some of you might have moved. So the image, G. So this would be frames per second if it was, let's say, 10, 20, let's say if it was 60 frames per second. What this means is that this would be 1/60th of a second later. Okay, 1/60th of a second later. So, so now we've introduced time. So now images are coming in and they're now changing in time. Now the question is कि आपके पास आपने यहाँ पर दिखाया कि there's a feedback, all right? Now let's say कि ये आपके पास, this was at time t and the output was as a time t, okay? Now, let's say the neural network is different or same, okay? Now you have the data and I'm only going to show you the subscript t. I'm not going to show you all the ij's, all right? So this is now t plus 1 and this is the output t plus 1. Now the question is, how do you think these two should be related to each other? This neural network and this neural network, are they related? If the weights that you've determined for this particular neural network over here, should those weights again be used over here? Should there be any relationship? Let's say that these were two different images. There was nothing in time, okay? अब मैंने इसको एक cat की image को यहाँ पर train किया. This is my example of a cat, all right? And then you took a dog, all right? Maybe bigger, something like this, all right? So you have two separate images. Are the two neural networks, well, are they related? Are the inputs related? Are the outputs related? Are the weights related? So if this was a different feature, so this was not a cat, this is now a dog, all right? So there's no direct relationship over here. But let's say if this was the same image of the cat 1/60th of a second later, and this was a video. So the cat probably moved a little bit. So now is there a stronger relationship? Definitely, right? So now there's a much stronger relationship because it's the same image which is slightly moved, okay? So you can see that the dependency is a lot stronger if it is time-based, okay? If it's a sequence of data. Now let's look at different types of examples जहाँ पर ये time dependence involved होता है, okay? So can you tell me what are the, can you think of examples? So आपने voice बताया. Is there a relationship between, let's say, what I'm saying now and what I'm saying earlier? Hopefully, yes. There's, there's some natural progression about what I'm saying. What other examples exist where there is time dependency? It could be video, as I said. So a series of video images are related, but think of other examples in daily life where there's time dependency in the data. Sorry? Road traffic. So if you look at, again, that's video. So you're capturing a series of videos on the road. It could be video, it could be road traffic, it could be a cat running, it could be sports, it could be anything, but that's a basic one category, which is video. Now think of something else. Sensor data, okay, very good. So this course is about sensor data, right? So IoT, all of IoT is actually all time-based. So so in this course, actually, we need to pay special attention to all the time-based data where there's a time series, okay? So time series, and you can see that time series is definitely there in all IoT, all sensor data actually looks like this. So if you have, give me an example of a sensor data. So temperature, let's say this could be temperature in a room and you're looking at time. So clearly the temperature is going to either come down and it's going to be a cyclical relationship, right? So every night is going to come down at 12 noon is probably when the sun is up, it's going to be hot and so on, or if it's AC is on and so on. So you have different cycles. And the relationship between this downward trend and this upward trend exists. So you know that if you look at the day temperature, you know that at night the temperature is going to be falling, okay? And so on. Other examples of data. Okay, GDP. So for those of you who are economists, you can see that all economic data is all about, or financial data is all time series data, right? So if you're looking at the GDP of this country, or if you're looking at the growth in the population of this country, if you're looking at inflation, if you're looking at the stock market, all of this has a time dependency. Okay, so all of that comes into a time series data. Other examples. So biological data, very good. So if you look at health, okay, so your blood pressure, if you look at your blood pressure, if you look at various, health data, they will all be related. Okay, there will be a time series. If you're doing exercise, suddenly your, certain things will change. Your BP might change. Your, pulses might change, and so on. Okay, so if you want to do any of that prediction, and this is a huge body. Okay. So if you want to apply for all of this data, which has a time dependency, or it doesn't necessarily have to be time dependent. Well, it has to be time dependent, but it could be represented as sequences. For example, if you have natural language, okay. So if somebody is talking, and as I said, example of how are you? This is not. This could be given as a set of sequence. Okay. So how is the first word that's being given, then are, and then you. Okay, so this is it's not necessarily given in terms of time, but it's given as a set of sequence. Okay, so you can think of all of these as areas where there's either time dependency or there's a sequence. Okay, so these are some of the examples. Here is, the stock market. You could have sequence of data predictions. Here are some other examples. So here's image captioning. For example, if somebody is, and this is all from natural language, so let's say you're trying to caption this particular image, okay? So that requires NLP. In other words, you have to come up with a caption which is explaining this image, and this says boy kicking a football, right? So there is some sequence relationship between, you can't say football kicking a boy, right? That would not make sense. So that sequence is important, okay? So video frame prediction that we've already talked about. Language translation. So if you look at Google Translate, it actually uses the same technologies that we're going to be talking about. So I just put that into Google Translate. I said this small cute cat came up with choti pyari billi, right? So, so this is, all of this is based on the same technology. Okay. If you're doing sentiment analysis, this is another example. So for example, you could be doing something like, if you have a sentence which says, Joe's dog is cute versus Joe looks like a dog, right? And if you're trying to say, what is the sentiment over here? Is it a positive sentiment or is it a negative sentiment, right? So clearly, this is a positive sentiment and here is a negative sentiment, right? So you want to come up with a vector which explains this particular sentiment. And this is, the whole area of sentiment analysis. So in all of this, the sequence of data is very important. Where is dog coming in? Where is Joe coming in? And so on. Okay. So So the question is, okay, how do we actually address this issue? Okay, so how are we going to change the neural network so that we can actually address the issue of time? Okay, so you've got some ideas. आप लोग ने कुछ चीजें बताई पहले कि you could do something like a feedback. Okay, so now how do you do a feedback? So you can see that there is a relationship x of t over here and x of t of plus 1 over here. Okay, now how should the feedback be coming in? So here you were showing a feedback going like this. Okay, so let me try to redraw this. Let me just draw it over here. So here, let's say you have a neural network. Okay, and this is time xt and this is yt. And here's another neural network. And this is xt plus 1, and this is yt plus 1. Okay. Now remember that this has a hidden layer. Okay. So if you remember, if you think about it very simply, you have an f over here, which is the summation of all of these data, and then you have a y over here, which is the output. Okay. So where do you think, how do you think these two should be related? Should yt plus 1 have an impact on yt? No, that's counterintuitive because you not normally go back in time, you're going forward in time. So it shouldn't be this way, it should be clearly this way, right? So yt should have some impact on yt plus 1, okay? So what do you think should be the architecture of this network? So let's say this is the input layer, this is a hidden layer, and this is the output layer. This is another input layer, this is another hidden layer. Let's assume that this is a shallow network with only a hidden layer, okay? So this is the network. This is x of t plus 1, y of t plus 1. So how do you think these should be related to each other? So say that again. Who is, sorry, aap kuch keh rahi hain? Sorry, okay. No, who said that? With your mask, I can't figure out who's saying what, okay? So just raise your hand before you say something so I know who's speaking, right? Okay, so y should become the input for the x layer. Should it replace xt or should it supplement xt plus 1? आप बताइए, should y of t replace xt plus 1 or should it supplement xt plus 1? Supplement, so it should hopefully be something like यहाँ पर इसको add होना चाहिए. So in other words, the input over here is not just going to be x of t plus 1, is going to have a whole series of inputs which are going to be over here. Well, actually it should be over here, right? Because xt to ye hai, and now you're taking this output and you're feeding it over here. Would everybody agree with it, or are there other architectures? Does this all make sense? This should be one of the architectures. Can people think of other architectures? So remember, there is an output over here as well. Okay, so this is the final y values. Sorry. Yeah, so the question is, how would there be a dense relationship or not? Would it be a full matrix? In other words, for every output over here, there, I'll put it like this, which means it's a dense relationship. Okay, but what normally is done is that these outputs, if you think about it, there are weights over here. Okay, and I'm going to now show you a slight change in notation so that it becomes a little clearer. I'm going to start introducing some notations, and before that, let's take a look at the normal feed-forward network. Okay, so the feed-forward network looks something like this. There are no loops, there's no feedbacks. The only feedback that's going on is for updating the weights. Okay, but as the data flows, the data is only going forward. All right, so this is called a feed-forward network. Okay, Now let's look at, as I said, the issue over here, the problem over here is that there is no connection with t minus 1. Okay, so in other words, if you have this particular output over here at yt, and earlier you had this particular output at yt minus 1, clearly there is a problem because you suddenly your dog is converted into an elephant. Now it could be possible that it was a different frame, but the chances are that that shouldn't happen. Okay, so what we're going to do is we're going to introduce some parameters, okay, so that we can actually capture this particular scenario. Okay. Okay. So now what we've done is, first of all, we've added time. Okay. We've already seen that. What we've done is we've added time over here. Okay. Now we're also introducing the input weights and the output weights. Okay. Now normally we didn't really take a close look at this earlier because this wasn't really necessary. But as you can see that in the input, at the output you also had some weights. Before y was calculated, when f was calculated, it was a series of input weights, which we showed over here, and then there was also output weights. Okay, so we'll try to differentiate it by calling it wi for input weights and wy, which clearly is linked with this y as the output weights. Okay, so what should be the equation for these? Let's try to figure this out. So what should be the equation for, let's say, h of j? Now, I made a small change notation. So, and this is keeping in view of the changing notation, because RNNs, as we go at looking at different architectures, notations will change. Okay, so somehow you've got to be able to keep track of the changing notation. So earlier we had used f over here. Okay, now we're going to use h because h is now the hidden layer. Okay, so we're going to replace f by h. So now let's look at the output. Can somebody tell me what would the equation for h of j? So now j is each one of these. Okay, so this would be, for example, h1. This would be h2. And this would be h whatever, hj in general. Okay, so can somebody tell me what would be the equation for hj? Now notice that I've called this wi is the input weights, wy is the output weights, and each one of these has a parameter wij. Okay, so in other words, this would be w11. Okay, this parameter would be w1, w12, right? So you get the idea. So can somebody tell me what would be the equation for hj? Summation of wi ij multiplied by x what? xi, very good, plus the bias. So there is a constant same bias, so let's call this bh. Remember, the bias is the same if it's an image. Okay. What else? So this is good. Let me just make sure I have it right over here. Okay. So just small correction. I'm not exactly replacing it with a y. I'm calling this as the output over here. Okay. So this is the intermediate result. So it's not f, but it's y goes to h. So what would this output over here be? We're calling the output of this neuron after the activation as h. Okay. So what is missing over here? The activation. Okay. So the activation now, we could call it sigma, we could call it something else, but generally what we're going to refer to it, keeping in view with this new notation, we're going to call it GH of this. Okay, so this is a non-linear activation. Okay, and why do you think I'm calling it with a parameter h over here? Because this is the non-linear activation for which is associated with the hidden layer. Okay. Now, can somebody tell me the equation for y of k? By the way, the summation over here is over what? I or j? It's going to be over I, right? Okay, so now let's do this. What is this going to be? Wy. So we're going to sum over all j. Okay, so this is going to be j to k multiplied by h of j plus the bias b of y, right? And then we're going to, the output has an activation as well. So it's going to be g of y. Okay, so far so good. Oh, sorry, g of y. Okay, so this is the complete equation for the outputs, right? Now we're going to use a slightly simpler notation, and it's going to be in vector form. Okay, so instead of writing all of this like this, the vector notation is going to be a little simpler. We're simply going to write as h is equal to g of h, the activation, and we're going to say wi x plus b of h. Okay, and can somebody tell me the equation for this? For y is going to be g of y applied on the wj w of y, right? wy times h plus b of y. Okay, so this is going to be a vector notation, which basically says that this is a dot product. Okay, so in other words, this is going to be w1 h1. Sorry, it's going to be wy 1 times h1. Well, you have it right up here. So it's exactly this. Okay. So this equation is simply converted into a vector form. Okay. And if you want to understand what this is, you can see from this particular equation, this is exactly what it is. Okay. It's what is called a dot product. So far so good. We've got used to a new notation. Now what we're going to do is we're going to add time. Okay, and we're going to use the same vector notation, but now we're going to add time as well. So what are we going to have over here? What is the output going to be for h? So now we're using the vector notation. So हमने पहले क्या किया था? We simply had h, right? So now what is it going to be? ht is going to be equal to summation हम नहीं करना क्योंकि हम vector notation इस्तेमाल करना, simple notation. So it's going to be g of h multiplied by wi x xt. Now why did I add a t over here? Weights same रहेंगे. Very good. So we're going to, but the t is going to change. Okay, and then you're going to have sorry, b of h. यहाँ पर t लगाना है, यहाँ पर b नहीं, because it's a weight. Okay, so the weights are going to remain the same. So you can see that we added time in two places. Okay. Similarly, you can see that y of t is going to be equal to g of y times wy times h t plus b of y. Okay. So far so good. Now what we're going to do is we're going to make it what is now called a recurring neural network. Okay. In other words, what you just earlier said, because now we have some notation, we can actually now start writing the equations. We saw that we want to convert this particular system and write it in terms of an equation. Okay. We want to take the output over here and we want to feed it in over here. Okay. Now, हमने यहाँ पर अभी देखा है कि there was an H was the output of the hidden layer, and Y was the output of the subsequent layer, the output layer. Okay. Now the question is, should we take the output from here, or should we take it somewhere over here? Which do you think is better? Is there a better solution, or are they both the same? Should we take this, or should we take the output H? We could take either one of them. We could take both of them as well, right? So in other words, the input over here could take either the output Y, or it could take the output H. And do you have any thoughts on which one should we take? Okay.
Like for example, if we are applying it to so in that case, first the initial word should be decided before getting to the next word. The decision, for example, we are deciding about the boy, the word boy. First of all,
so let's say this output was, you're saying the boy, that example was a boy kicking the ball, right? So we had an over here, and then this was, hopefully this should be a boy over here, which you're trying to select. So what you're saying is that the output should be fed in.
Because is the article and then the subject.
Right, right. So that makes sense as well. Okay. Practically, the way RNNs are done is that they don't take the output normally. Okay. They take the output of the hidden layer, because all they're trying to do is they're trying to link these two. Okay. And they're saying is that if you have the output of the hidden layer, that is sufficient to link the two. Okay. But you could have an architecture which takes the output as well. You could have an architecture which takes both, but it becomes too complex then in that case. So what we'll see over here is that we're going to we're going to combine these. As I said, this is at xt minus 1. Okay, this is y of t minus 1. This is the subsequent input. This is the subsequent output. So what we could do is take this output, okay, feed it in over here, or we could take this output, or we could feed it in over here. Okay. Question is, which one should we take? And as you suggested, it could be either one of them, but practically speaking, it's this particular layer which is taken as the feeding in. Okay. And clearly it has to feed in over here. Well, there could be other solutions as well. You could say that, why do we need to feed it in over here? Why don't we directly feed it in over here? So there could be two possible other solutions. You could feed this in over here, or you could feed this in over here. Okay, so there are A, B, C, and D. I can see 4 possible architectures or a combination of them. Okay, but in practice, what is actually done is this particular option. Okay, these aren't really used. Why are they not used? Maybe you can think about it and investigate this, and you could come up with a different architecture in one of your research papers and say, well, I'm going to use a different architecture. In all of deep neural networks, there is no single architecture which is always the best. But people have experimented and found that some are better than others. So this by itself is only feed forward. So this thing is just feed forward, all right? But when you combine this with the subsequent one, this becomes a recurrent neural network. Why? Because you're basically taking the input of the previous data and you're using that to improve the same neural networks. In other words, this neural network at time t is going to take the input from ht minus 1, okay, and it's going to improve the neural network. So as you train it over a lot of words, right? So suppose you take, as GPT-3 has done, it's taken the entire Wikipedia and it's dumped it into these networks. and it's trained it so that it can actually speak. Some of you might have heard, there are, you've heard of the famous examples of how do you actually test, how do you test if an AI is actually, proper AI, okay? So you can actually have a conversation with it, and if you can't figure out whether it's an AI engine or it's a real human being, then it shows that, it's got really artificial general intelligence. So in some of the examples that you might find for GPT-3, there are conversations, proper conversations, lengthy conversations in which the not the person, but the AI engine is actually having a proper conversation, which is almost sometimes hard to depict whether it's an AI or not. So basically what you're saying is that if you feed it enough data, it will be able to figure out what the next word should be, okay? And should be able to then start doing things like image captioning, natural language translations, even responding to questions. All of that becomes possible because you fed it enough questions and answers for it to be able to say, okay, if I get this kind of a question, then I'm going to get this kind of an answer. But it's not just repeating things, it's actually creating answers, okay? Sometimes I think about how dreams work, all right? This is going a little bit on a tangent. But if you think about how dreams work, when you have a dream, is it always a replica of something that you've actually had in your real life? It's not, right? You come across a new situation which you've never had in your life, right? It's a completely new situation. So how is that being created? If you think about it, how do you think that image is being created inside your brain? We'll talk about this later on when we talk about GANs. Okay, it's a very interesting area, but basically what's happening is that your mind is actually creating images. Okay, it's not reproducing them, it's creating new images, but it's creating them based on your trained neurons. Okay, so it knows, sometimes I see, family relatives. Okay, so it knows those images, but the situation is different. It's not a replica of what you might have come across, but it's combining things in different ways and it's coming up with new dreams. Okay, so it's a whole, it's very interesting if you think about it. There's a lot of synergies between neural networks, neuroscientists, and what's going on over here. Okay, and most of the good networks, most of the good architectures are actually bio-inspired. Okay, that was the question. Yeah. Yeah, well, that's another topic. Talk about that later. So anyway, so we've added time, and I've said this is the architecture that we're going to do. So this is the architecture that is actually used. Okay. So here, what you've already seen is that we're going to take HT. Okay. We're going to take WIXT. Okay, and we're going to multiply it with a new set of weights. So we're not going to use the same weight. So it's आपका जो सवाल था कि is it going to be a dense network? Yes, it's going to be a dense network. And we're going to take a different set of weights and multiply it with the output that we got over here. Okay. And then we've got the BH. So we've got BH over here. This portion is the same. This portion and this portion we've already seen. Okay. Now what we're doing is we're simply adding an input from the previous, the output of the previous hidden layer. Okay. So this is what we've done over here. If you look at the output Y, okay, the output Y has not changed. Okay, the output Y is simply equal to the GY multiplied by WY. Okay, the weights over here multiplied by H of T plus BY. Okay, so there is this small change. This is the small change that we've done in order to be able to create what is referred to as recurrent neural networks. G. Yes, so what you're doing basically now is training this entire network. So now the question is, how is this going to be trained? Okay, and if you think about it, normally what we did was we had backpropagation. Okay, so we use the output over here to train these weights. right? Now, what do you think when we trying to train this entire network, and we have a sequence of inputs? Okay, so we have a sequence of all of these. Let's say this is this particular set. This is this set. This is at x. This is at time t. This is at time t plus 1. This is at time t plus 2, and so on. Okay, and we have a long sentence. Okay, a boy kicking the ball. All right. So here's your sentence, and now you're trying to train it. Now, how do you think this is going to be trained? How is the back propagation going to work? Will there be any relationship between this output and the training that's going on over here? How is the training going to be done? It's a tricky question. Yeah, so basically what you're going to do, well, the short answer is you're never going to use grammatical rules. Remember, in neural networks, you never give it any policies beforehand. The network, based on the data, on the training data, automatically adjusts the weight and trains itself. So you don't have to figure out, you know, in the olden days, if you're trying to write something which is write English, you'd have to feed in all the possible grammatical rules, right? It would have to know what a verb is, what a noun is, what, you know, all of those millions of rules, okay? But you don't have to do that anymore, because now you give it enough data, and just like a child learns, when you're a child, nobody actually taught you, okay, Urdu ka grammar kya hai, English ka grammar kya, right? But when you're learning a foreign language, sometimes you have to learn it through grammar. But as a child, when your neurons are developing, you just simply have a lot of input, and you have a lot of corrections, right? So when you use the wrong sentence, your mother will probably have corrected you, nahi, is tarah nahi kehte, is tarah kehte, right? So that was the positive feedback. That was the label. And somehow when you made enough mistakes and enough times you were corrected, your neurons eventually figure out that this is how you speak, okay? And that's how most of us learn a language. We don't learn it through grammar. So grammar is not going to come in over here. आप कुछ और कह रही थी? So grammar is not going to be used, okay? But it's going to learn, it's going to figure out how to speak, okay? So, exactly. So it will learn without the grammatical rules, but it will learn how to speak simply from listening to others. Right. Right. So you have to give it enough data, and now for it to be able to train, so if you're doing image captioning, you'll have to give it enough images of boys playing with football, and to be able to give enough label data that, you know, this is a label where a boy is playing with the football, another one which says a boy is kicking it, another, and so on, you know, various variations, and it'll be able to figure out, okay, what is the appropriate caption for this particular image? Is it a playing, dribbling, kicking, heading, whatever it is, and is it a boy, is it a girl, and so on. It would be difficult because now you have to give it a lot more data, and you have to give it time series. So now you not only have to give it a single image and say this is a cat, this is a dog, but now you have to say how does that image, how does the caption of that image actually relate in time? Okay, so you have to convert that single image of a dog or a cat or a boy, and now you have to relate the fact that there's a boy, there is a ball, and there's a verb as well, you know, in a sense, there's a verb that he's kicking the ball, okay? So all of that has to come in. Is there a question online? No, okay. So the issue is that how does the back propagation work? Okay, so the way it works is a little tricky. Is first of all, you unfold this network in time, okay, which is basically what we've done over here. This is also an unfolding in time. So this is how time is progressing. We're simply showing it in the horizontal axis, okay? So this is how it's normally going to be shown. It's going to be shown horizontally. Sometimes it's also shown vertically, okay? And now this is all time, okay? So this is x1, x0, x1, x2. This is the output at time 0, output at time 1, output at time 2, okay? So if you have something over here which says a boy kicking the ball, okay? So now to be able to figure out how to train this network, there's something called, and it's a little complex, it's called backpropagation through time, okay? Backpropagation through time, okay? In other words, what it's going to say is that when you're training this particular WI, you have to not only take a look at the output at time y0, okay, but you also have to look at the outputs at different times, okay? And there are different algorithms which either will do it all together or they will do it in sequence, okay? Some of the more recent algorithms, what they do is they give the entire sentence together and it tries to figure out what's the best neural network. The earlier algorithms, which was what basically RNN does, is that it would do it in time sequence. Okay, it would do it one at a time. In other words, when it's weighing this, okay, it would look at the past input. And when it's finding out the weights over here, it's not only looking at the current output, but it's also looking at the previous outputs. Okay, it's looking at all the past data as well. So basically what happens is, if I look at this, I'll show you how it looks like. So this is, so let me just show you what it looks like. So here's the loss equation. Okay, normally what you would have is you have a particular loss, okay, and you're trying to find out how to update it, right? So you would say the loss at time 0, okay, is equal to the output at time 0, the derivative of the output with respect to h, and the derivative of h with respect to wi, okay? So this is only looking at this particular portion. This is how it used to be done, right? So this is not new. Hopefully you remember this, right? Does everybody remember how we did backpropagation? Okay, we took a sequence of derivatives. Now, how do you think this is going to change? So let me tell you the answer. So the way this is going to change if you're doing backpropagation through time is that when you're updating the loss at time 1, okay, so this is time t is equal to 1, you're not only going to look at the output at time 1, okay, but you also, and you're going to look, but you're going to now take the derivative of the output with respect to h1, okay, so this is h1. You're going to take the derivative of y1 with respect to h1, and then you're going to take the derivative of h1 with respect to h0. Okay, now remember, h1 has an equation with respect to h0. Okay, you remember that, right? So we saw that a little while ago, that here is the equation. H of t is related to h of t minus 1. Okay, so now you have to take a derivative of h of t with respect to h of t minus 1. What will you get? You will probably get these weights. Okay, so those weights will be updated accordingly. Okay, and then what you're going to do is you're going to take the derivative of h0 with respect to wi. Okay, so now you can see that as time progresses over time, the longer the sentence, okay, the more complex the backpropagation through time becomes, right? And what happens when things become very long? We talked about a problem. There was a problem which I referred to as the something gradient problem. The vanishing gradient problem, right? Vanishing gradient problem basically said that if these derivatives become very small, okay, then the impact on the subsequent improvements, remember this is just the derivative, this is the derivative. Then there's going to be a wn plus 1, the weight is going to be, the change in weight is going to be the old weight plus the change in the derivative, right? So it was wn plus 1 is equal to wn minus the learning rate times the derivative of wl with respect to w, right? So we only talk about this. Now, if this becomes extremely small, The longer you have the sentence, the smaller this derivative becomes, okay, the gradient. And if it becomes too small, it's not going to have any impact on the updates. So essentially, the updates are not going to change, okay? So the question is that this is one of the biggest drawbacks of this particular algorithm, which is the RNN algorithm. And this will lead us to a better solution. Let's see what time it is. We've got 10 minutes. Let's talk a little bit about how could we solve this problem. Okay, so the problem basically that I'm identifying is that there's a vanishing gradient problem. Okay, if you're doing backpropagation over time, then RNNs are okay. They will be able to solve the problem. But think about, and this is going to lead us to the next topic, which is something called LSTMs, which stands for long short-term memory. Okay, why does it have both long and short? Don't ask me. Okay, but somebody figured out that we'll call it long short-term memory. But there's a hyphen between short-term and long. So the problem with RNN that we've already seen is that there's no long-term memory. So here's an example. This is a classic example that's always given. So I'll repeat that. Suppose that you have a very long paragraph. Okay, you say you start by saying I traveled to France, I met many people, I went to blah blah blah, and at the end of the long paragraph, you want to predict this particular portion. You say I learned a lot of something. Okay. Now imagine this should be linked to France, right? You're not going to say I learned a lot of German, right? Because obviously it should have somehow remembered that at the beginning of that entire paragraph, you started by saying I went to France. Okay, so it has to be able to relate this thing which occurs, let's say, after 100 different words, and you have to relate it to this. Okay, now again, there's going to be backpropagation through time. Okay, and hopefully it should be able to figure out that this word over here is French and not German or something else. Okay, why? Because it should remember that we are in France. Okay. Now the question is, how do you do that? Using RNN, the backpropagation through time is the gradients are going to become extremely small. It's not going to be able to learn very well. Okay. Another example of this could be, for example, you started off by saying a boy, right? A boy went to France and so on, and then somehow, somewhere in the middle, you say that you change the gender, and you say that the boy met his a girl or whatever, and then you now started talking about, and earlier we were talking about he, right? So everywhere you were talking about a pronoun, you were referring to the boy as he. Now all of a sudden, the individual changed, and now you're different part of that paragraph, and you're talking about a female. Now hopefully, if the neural network is properly trained, it should have been able to figure out now the gender has changed, and now the pronoun should be she, right, instead of a he. So somehow it needs to be able to remember certain things. Okay. Now, how do you think you could actually change the neural network so that it can have long-term memories? So now we're talking about something different. We're not just talking about a simple recurring neural network. We're trying to have some kind of a memory in it, which can be used after a long time. So how do you think you can do that? How would you change this neural network? Okay, how would you change the neural network? So far what we've seen is that we can link them up in time. Okay, we can somehow feed this output in, and we have new input coming in, and somehow they can be linked in time. But now the issue is that the gradients are becoming very small. It becomes very hard to have something over here. You started by saying France over here, and much later you're trying to figure out whether this should be French or German. Okay, and the linkage between these two have become too small. The gradient has become too small. It's not really learning that. It's not really picking up the fact. It's already forgotten that you were in France. Okay, so it's not going to be able to do that if it's a very long paragraph. So can we have some some solutions. G. Okay, so here's a good solution. So what we could do is we could have shortcuts. Okay, so you saw this earlier somewhere, that where did we see this? We saw this in ResNets, right? So ResNets are basically saying that in ResNets, was that in time, the shortcuts? Was it in time? It wasn't in time, it was all in the same time. So, but here what you're saying is that let's link these up in time. So this is a novel idea, by the way. I don't know if anybody's actually done this. What you're saying is let's take the output at time 0, and this is at time t, let's say at time t is equal to whatever 10, and let's link these up, have some kind of a shortcut, which would sort of partially solve the problem. Okay, because now you can see that it will remember, it doesn't have to go through all these gradients. It can have a direct relationship and say, okay, oh, great, I remember that this was France over here, so this has to be linked over here. So this is a good solution. In fact, I hadn't thought of this, okay? I don't know if there's architectures which use this or not. This is not actually what is used. I'm sure there is somebody who's experimented with this, but it's not directly used. Any other ideas? These are good ideas because actually you can do research. You can take a topic, you can modify this architecture, and you can use this particular thought, okay? And maybe you'll come up with something else just perhaps working better. It's a novel idea, okay? How else can we do it? Okay, let me introduce some more notation, okay? I hope I'm not overburdening you with a lot of new notation. How much time do we have? So we have another 5 minutes or so. Let me introduce a slightly modification of the notation. And okay, so it doesn't delete that. Anyway, so I'm going to make a slight change in the notation. So far we've looked at RNNs, and RNNs are typically depicted in this particular manner. Okay, you've already seen this. I'm going to show it in a slightly more detailed fashion because now that we're talking about a new architecture, LSTMs, it requires a slightly more detailed architecture. Okay, so if you're looking at this, you can show the same architecture in the following way. Okay. Now, if you can remind me what were the equations. So we had an equation for H1. H of t was equal to what? G of H times W I X plus B, I think BI. X of t, very good, plus B of H, right? So now we can write the same equation. Here there's a slightly different notation. Okay, sorry, this was without the time, right? With time, what did we have? Plus, it was related to the previous time, right? T minus 1 WR, right? That was the only difference. Now it's linked to the previous one. This is what is shown over here. Okay, that H1 is linked to H0 by WR. Okay. We're going to show the same thing over here, and we're going to show H over here. So this is H of t. Okay. This is H of t minus 1, right? And this is, and here they've shown tan H over here. So practically speaking, in order to, now tan H is something I haven't spoken about. We've spoken about sigmoid, we've talked about ReLU. Another activation function is called the tan H. Okay, it basically looks like this. I'm not going to bother with you with the equation, but basically it looks something like this. It goes up to +1 and -1. Okay, now sigmoid goes from 0 to +1, right? Now where do you think tan H is used and where do you think sigmoid is used? What's the difference between these two? If you use a sigma over here versus a tan over here, what do you think is the output going to be? How are you limiting the output if you use sigmoid versus tan H? Right, so if you're using tan H, it will allow negative values up till -1. It will squash large values to -1 to +1. And sigmoid will squash it between 0 and 1. Okay, so that's a basic difference. Now in RNN algorithms, normally you use a tan H. Okay, so you use a tan H. If you can read this over here, it's a tan H. And basically what you're doing is you're squashing the output to be between -1 and +1. Okay. So if you look at this notation, where should I put in the weights? I've shown H of t, okay, over here. And this is X of t, okay. This is H of t -1. And H of t -1 is showing up over here, right? It's being added over here. So where should I show Wi and where should I show Wr? What am I going? What should be over here? Wi should be over here, and what should be shown over here? Wr. Okay. So this is a new notation, and you can, if you have y over here, y of t, where do you think Wi is going to be shown? Over here or over here? On the second part, right? It should be shown over here, Wi, not over here, because if you showed it over here, it would imply that ht plus 1 is not dependent on Wi, which is it is not. Okay, so it's not going to be shown over here. Over here, it's going to be done over here. So basically, this is a shorthand notation, which basically shows how you can show this entire complex equation in terms of a simple notation. Okay. So having introduced this notation for our RNN, so this is an alternative way of showing an RNN. It basically shows how these are cascaded together. Okay, just like it's shown over here, but we're going to use this notation because now we're going to introduce something called LSTM. Okay, so you can see this is the equation. H of t is now equal to g of h. The only thing I've changed is that instead of g of h, I've replaced it with a tan h function. Okay, so everything else remains the same. Okay, so this will now start a new topic, and I think I'm going to stop over here. 8:59. Okay, so we'll start up the topic of LSTMs next time and try to see how we can figure out how to actually have long-term memory, okay, which is called long short-term memory.